Hello, and welcome to my report on Lab 4, a macroscopic view of DC and RC circuits. In this lab, we were asked to calculate the properties of different steady-state and RC circuits and produce digital models for these circuits. We recorded data from the models and compared the outputs with our calculated values. We also recorded data from an RC circuit to predict the time constant. The first circuit we made in this lab was a series circuit which contained two 1.5 volt batteries, two ammeters and two resistors, one with a resistance of 47 ohms and another with a resistance of 100 ohms. We were asked to predict the current which the ammeters would read. To do this, I divided the voltage of the two batteries by the total resistance in the circuit. This gave me a value of 0.0204 amps, which was reflected in the model. Next, we were asked to reverse one of the ammeters and see what would happen to the reading. In this circuit-making software, the reading was still positive, but I think in the real world we would see the reading be equal in magnitude but negative. The next change to the circuit we made was to replace one of the ammeters with a voltmeter. A voltmeter records the potential difference across its probes. Due to the combined voltage in the batteries, the potential difference at this point in the circuit is 3 volts. The ammeter's reading has dropped to 0, however. This is because the internal resistance of the voltmeter is incredibly high, and as the current is being forced through what is effectively a very high resistance resistor, the value of the current becomes very close to 0. We then connected the circuit and measured the potential difference of 8 different sections of the circuit. There was a positive potential difference of 3 volts across the two batteries. The wires were modelled such that their resistance is 0 ohms. The potential difference across the 47 ohm resistor was negative 0.959 volts, and the potential difference across the 100 ohm resistor was negative 2.041 volts, which is displayed on the graph. In this next step, we attached an ammeter in parallel to the 100 ohm resistor. When we did this, we saw the current in the circuit increase. This is because the ammeter has comparatively low resistance and the electrons in the circuit will take the path of least resistance. As we have effectively removed the 100 ohm resistor from the circuit, the current increases. Next, we looked at RC circuits. Here, we connected a 9 volt battery, a 10 ohm bulb, a 200 millifarad capacitor, and an ammeter in series. As this is an RC circuit, over time the current of the circuit changes. Using the bulb as an indicator, we could see that over time the current became 0 as the capacitor charged. It took 10.5 seconds for the capacitor to charge up in this setup. It also took 10.5 seconds for the capacitor to discharge. Next, we replaced the 10 ohm bulb with another which had 20 ohms of resistance. This time it took 18.15 seconds for the capacitor to charge and the same amount of time for it to discharge. The last experiment we performed was to determine the constant of an RC circuit which contained a 9 volt battery, a 200 millifarad capacitor and a 30 ohm light bulb. We used a voltmeter to measure the potential difference across the capacitor at different time intervals. The data from that experiment is displayed here. By plotting the natural log of the potential difference divided by the potential difference at time 0 against time, we're able to determine the time constant for from the slope of the graph. We expect the slope of the graph to be the negative reciprocal of the time constant. As you can see in the graph, the slope is minus 1/6. This tells us the time constant has a magnitude of 6 seconds. This is the time at which the voltage difference has dropped to 1 over E of its original value. Lastly, we answered a couple of questions. The first of which asked, if we were to do the lab in real life, what would be different about the ammeter compared to our simulated one? In real life, all components have some resistance. By including an ammeter, we would not be able to measure the exact current. Simply by including it in the circuit, we will change the value slightly. The next question asks, what would happen if you charged a capacitor with a battery in real life without a resistor? In the model, the capacitor would charge instantly as there is no resistance between the battery and the resistor. However, in real life, all electrical components contain some resistance. This means that it may still take some time for the capacitor to charge. If the resistance was very low, the components would likely be damaged. This concludes my Lab 4 report. Thank you for listening.